Good morning. How's everybody doing today? Here we go. Let's see. Do we have anybody in the chat today? Just say hello if you're here, of course. And I'm not really expecting anybody to be here. So it is a holiday. So happy Martin Luther King Day. But I did want to still go ahead and record it just because this is a good time for me. Hello, welcome. Glad to have you here. And so, of course, just ask questions and I can go over anything. So it looks like everyone's doing well with the course. People have been turning in, the quizzes, the labs. So the only tricky thing was people had to find the videos. But I think people have found the lab videos now. So that's good. And again, if there are any questions, just put them in the chat. All right. So let's go ahead and start chapter 2 here. And so now we're going to be taking a closer look at all of our atoms on the periodic table and going into the atomic structure. And so let's review. So we had said last week that an element is a pure substance that cannot be broken down. And so if it's a pure element, when we were talking about classifying matter, right, it has to be on the periodic table. And of course, don't forget your diatomics. And so we wrote this down last time, but you want to write this down again or highlight them. So we had our diatomics. So hydrogen, we can circle them. And then the other one, they made that 7 pattern there. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So all those are still considered elements. And so this is their elemental form, so basically how they're found in nature as a pure substance. And so anything else, so a compound, as we'll later see. So let's just jump ahead. So a compound has to contain 2 or more different atoms. Well, let's go back to elements before we get too ahead of ourselves. And so just to kind of give you some context, here's the elements in the human body. And so obviously we're a lot of oxygen. So humans are about 70% water. And so if water has a formula of H2O, that's a lot of oxygen in there. And then, of course, any other oxygen containing compounds as well. Obviously, we're carbon based life forms. And so, why this is, we'll kind of get into. And so, carbon, I'll give you some hint as to why we're carbon based, but carbon has a smaller radius than expected, kind of our periodic trends, and we'll get into that as we continue talking. But carbon can also do a bunch of cool things. So it can bond with itself, so it can make double and triple bonds with itself and make these ring structures. And silicon, for context, is right below carbon, so we might expect that they behave the same, but they don't. So silicon can't do the cool stuff that carbon can. And so, again, there's a lot of research into kind of silicon and carbon analogs of highly reactive species. I won't go too down the rabbit hole or else I'll get too excited. But that at least gives us a hint as to why we're carbon-based life forms. And then, of course, if we're organic, right, organic compounds are carbon, hydrogen, and oxygen. And so obviously we have a lot of hydrogen in there as well. And then nitrogen is a part of a lot of different amino acids and functional groups like amines. So we have a fair amount of nitrogen. And then we have a lot of other elements in trace amounts. So obviously we expect to have calcium, Then there's phosphorus, sulfur, sodium, magnesium, as long as other transition metal elements as well. So manganese is also good, iron. So you have a few random ones. And so now to compounds. We said compounds were two or more different atoms. And so this could be, and if you're in the chat, you can list some compounds. But a simple one would be CO or carbon monoxide. And so carbon monoxide, you might be aware, is a colorless, odorless gas, and it comes from the incomplete combustion. So sometimes if you have like a faulty space heater, like people use those little, like, what are they called? The heater buddy guys, or like car camping. You have to have a carbon monoxide monitor just in case. It's good to have one around your house. And so the other thing we want to kind of familiarize ourselves with in this course is all the different ways that chemists show things. And so we have a lot of these ball and stick models, or the kind of more space filling, and they're all color coded. I'm also pulling out my molecule kit. And so I have a random piece here, but they mean things. We have blue for nitrogen, a black for carbon. And so you could kind of write down a general guideline over here. So red tends to usually be reserved for oxygen. We have oxygen here. So this would be water that's drawn. They just didn't draw out the single bonds explicitly. So sometimes, right, this one doesn't show bonding, but just more geometry and space filling. And then it'd be up to us to figure out single, double, triple. And then so notice, right, I knew that these were hydrogens. And so white is generally reserved for hydrogen. And so we said black was carbon. So black is always carbon. And so blue tends to be just nitrogen. And then we have other colors as well. And so you can have a green ball. So green tends to be any of the halogens. What are halogens? So we'll be going over all of this, but halogens are going to be, let's go back to our periodic table. Where's my periodic table? All these, group 7. So a lot of our diatomics, but these are called halogens. We'll take a full tour of the periodic table. I'll put in parentheses, fluorine, bromine. I'm looking. This kit is, you can have other colors as well. So it kind of depends on how many holes they have or what they're hybridized. But we'll get back into this. But you could have like orange, and that tends to be like phosphorus. Sometimes you might see a purple as phosphorus. And then yellow could be sulfur or other group 6. But that's just a basic kind of rundown. And so other than these types of models, let's draw out before we move on what this was. So we have 2 carbons. So carbon, carbon. And then to draw our hydrogens. And so we'll later learn that carbon always has to have 4 bonds. So there it's drawn. So this is drawn more explicitly with all the hydrogens drawn in. Organic chemists also kind of do this shorthand, which we're kind of seeing up here. And so what this shorthand means is I can draw this compound. And so this is actually, let's name this. So this is called ethane. And so you don't have to know how to name this compound yet. So this is an organic structure, but I'll let you know when naming when you need to know. So this is fun fact. But ethane could be written like this, just a line. And so this line means that each one of these points is a carbon here. And then you have to know that carbon needs 4 bonds. And so that's how you know you have your little hydrogens around it. Questions so far? And so looking at this kind of ball and stick model, we'll say, or not ball and stick, just our skeletal structures. So now we have just our skeletal structures. So let's go through this one. And on an exam, you might have to interpret a structure, like write the correct formula. And so for this one, this point is a carbon. Let's redraw this. So nitrogen, sorry. Don't have the best handwriting. Trying to go slow. So double bond oxygen, and then I probably should have drawn this. So that's a carbon. So right, this point's a carbon. So that's labeled here, nitrogen. And then this group out here, so that also means carbons. Now CH3. Now going around. So this is a carbon, just to be clear. This is another methyl group hanging off of that nitrogen. So CH3. So double bond. And then let's count. So this is a carbon and it has to have 4 bonds, 1, 2, 3, 4. So that doesn't have hydrogen. Same thing with this one, 1, 2, 3, 4. So that's okay. Another methyl group. So CH3. And then this carbon. So 1, 2, 3. So it has one more hydrogen. Just glancing. And so now let's write our formula. And so usually it's carbon, hydrogen, and NO. So kind of alphabetical order. So count with me our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. Then hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Double checking. And then nitrogen. So 1, 2, 3, 4. So nitrogens are always drawn out. So you have to draw those out. And same thing with oxygen. So 1, 2. So C8, H10, N4O2. Let's look at some other structures or other organic compounds and what they look like. So let's write the formula for this one. So take a minute, see if you can figure it out. At least get an idea what all those points mean. And so maybe you started to redraw this. So again, each one of these points is a carbon. So let's just start by doing that. So we should have a little ring with 6 carbons. And then we have to fill in the missing bonds. So again, carbon needs 4 bonds. Now we have to add 2 hydrogens to each carbon here. And so now we can count them. So we should have C6 for our formula, and then 8, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's practice some more. So this is cyclohexane. And again, I'm not expecting you to remember these names right now, but just to kind of give you a hint. So cyclo means a circle, so a closed chain here. And hexane, so hex stands for 6. So that's 6 carbons in a ring. And so now let's draw out regular hexane. So hexane drawn out in what I would call chemist shorthand. So 1, 2, 3, 4, 5, 6, and then always double count. So this is counting is super important in chemistry. Like just and that should make you feel good, right? Just basic counting, addition, subtraction, but keeping track of the little things in chemistry will bring you far. So let's just double count 1, 2, 3, 4, 5, 6. Excellent. And if we draw this out more explicitly, so now put it in a line. And just so you know, the 3D shape is kind of more like this because each carbon is tetrahedral. So it does kind of make a little squiggly. Here's kind of the 3D model. You get a sense for it. Right, 1, 2, 3, 4, 5, 6. Fill in my hydrogens. All right, and then let's get our formula. And so C6, but now since we have not a ring, a straight line, we should have more hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So H14. See, let's do another practice just so we feel okay. Let's see, what if I draw out? So I'm going to draw out this structure. So take a minute or so and come up with this formula. So let's see what we got here. And so this is getting another one of those rings. So we have carbons here. And so if you need to rewrite it, go ahead, and maybe I will, because I don't want people to be confused at home. So I'm just rewriting my little aromatic ring. Let's put the double bonds in. And so that means that all these other carbons have a hydrogen. And then this one had another carbon attached to it. So 1, 2, 3, 4, 5, 6. 5 of them have hydrogens. Right. So carbon, 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 carbon. And all these have hydrogens. This one doesn't, right? 1, 2, 3, 4. It already has 4, so no hydrogens. Now we're at this carbon. So this carbon only has 2 bonds. So we need to add hydrogen, hydrogen. So now we're at this carbon attached to our nitrogen. And then this carbon, 1, 2, 3. So it needs a hydrogen. And then this is our methyl group hydrogen here, or carbon and 3 hydrogens. And so now let's come up with our formula. Let's count our carbons. So carbon, hydrogen, nitrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then 1 nitrogen. I'll just leave it as nitrogen. And so, fun fact, this is amphetamine. So this could be used sometimes as like ADHD medication. And then does anybody know what separates amphetamine from methamphetamine? So this is amphetamine. We just found the formula for amphetamine. And so this is where if you start digging into like drug law, and to me it makes no sense as a chemist. But methamphetamine, I'll just redraw the structure. So it looks almost the same, except that on the nitrogen, it has an extra methyl group. So now there's the methyl group of methamphetamine. And so methamphetamine, it's really just the dosage too that makes, right? They always say like the dosage makes the poison. And so methamphetamine, and it all depends how you want to look at these sorts of things. And now I'm getting into the rabbit hole of drug stuff. But so methamphetamine technically kind of has some advantages in some ways, because with this methyl group that allows it to cross the blood-brain barrier more readily. So you need less medicine to, elicit an effect. But that's why it's illegal. And obviously, if you abuse any drug, that can cause issues, or if it's impure. Yeah, but that goes into like how fentanyl actually came around. Is like fentanyl was synthesized, so it's a synthetic drug, and it was made to try to give people the same relief with just a small dosage. But of course, now people are abusing and dying of fentanyl. So, anyways, drugs, addiction, always a tough subject, but chemically, there's not a lot of difference. It's always the dosage. All right, we can come back to these structures if we feel like it. So we can always do more review on Wednesday. Just let me know by email how we're feeling or by chat, of course. And so now let's look. So we want to get into the atomic structure in this chapter, especially before I get too excited about drugs and compounds. And so now looking at an atom, so what defines what an atom is, right? So we can go back to this periodic table. Okay, we have all these distinct atoms or elements, but what defines them? What makes them? What is an atom? And so now let's look at this. And, you may have gotten some sense, in school before, but now we're going to kind of work on getting a little bit more refined picture of our atomic structure. And so you may know this. So that atoms all have these subatomic particles. So they have protons, neutrons, and electrons. And so we'll look at those. And so protons and neutrons have nearly identical masses. So they have the exact mass here, but you can, round to the first 3 digits and they're about the same. So 1.67 times 10 to the negative 27 kilograms. But usually, and this will come up later, so chemists don't use this. So chemists use this AMU, atomic mass unit. So each one of these, so the proton and the neutron, are both about 1 AMU. And then if we look at the mass of the electron, so compare the order, the powers there. So we were at 10 to the negative 27 kilograms. And now we're at 10 to the negative 31 kilograms. And so often we say that the mass of the electron is negligible compared to, again, the proton and neutron. Negligible or 0. Right, 0 AMU. So you can move, the decimal place over 4 times to get to 27. And so that's why it's negligible. So we say it's 0 AMU, so we pretty much ignore it. But what is important is the charge of the electron. And so the charge of the proton and the charge of the electron are equal in magnitude, but opposite. And so usually we assign the proton be a plus charge, electron is minus. And then like it says here, the neutron is neutral, so no charge. And so this is a little summary chart. So again, there's the masses in AMU. So they have it more precisely. Again, you can see why the electron is negligible. You can see the charge here. So the charge is in coulombs. So this was determined from Millikan's oil drop experiment. He was able to get the charge of an electron. And of course, we just say that the electron is negative, the proton is positive. So each proton has a +1 charge, each electron has a -1 charge. And so now here is the next important piece. So the elements are defined by their numbers of protons. And so again, right, the number of protons defines the element. And so this kind of goes into, well, either nuclear fission or nuclear fusion, right? So either thinking about how the universe was formed or, may have been formed in that heavier atoms or lighter atoms combine to make heavier ones. And so that gives us, right, our heavy elements. or in a nuclear reactor, right, you're breaking down and changing the identity of your atom. And so that very rarely happens, right? So we very rarely change the identity of an element. And so let's go back to this periodic table here. And so these numbers then, these atomic numbers, so you can look at your key, but your atomic numbers should be in our upper left hand corner. And they just go in order, right? 1, 2, 3, 4, 5, 6, 7, etc. But this is the number of protons. And again, if you change the number of protons, you completely change the identity of the element. And so we can go down, let's look at molybdenum. So molybdenum has an atomic number of 42, and that means it has 42 protons. And so again, write that down. And sometimes you see this Z for atomic number. And so looking at this little schematic here, so we are looking at a helium atom. And so notice the center here, the nucleus. So the nucleus is just the center of the atom, and it contains protons and neutrons. And so in this case, we're looking at a helium nucleus. And so we have our 2 protons and 2 neutrons in the middle. And so in this case, they happen to be the same. But again, the 2 protons is what defines our helium element. And then most helium tend to have a mass of 4. So this is how we could write this symbol. So meaning our mass here, which we'll get into, and then our 2 for our atomic number, so our Z. So same thing. So this carbon is shown here as kind of our standard carbon with 6 protons in the nucleus, and then 1, 2, 3, 4, 5, 6 neutrons as well. So 6 neutrons. And so this is known as carbon 12, so our usual carbon. Let's get into that more. And so we see they're arranged by their numbers. So we'll get into the whole why are they in these certain columns as we continue our tour. But let's go into other definitions. So I was kind of saying this is our standard carbon, right? Our standard helium. Well, what was I alluding to? And so let's talk about isotopes. Can anyone name some examples of isotopes, or are you familiar with any isotopes, what they might be used for? And so if the examples come to you, just type them in. Well, let's look at this first example here and then talk about some other ones. And so the first statement, so all atoms of a given element have the same number of protons. All right. So we said that, right? We can recap. All right. So our protons, our number of protons will always be here for that element. But then it goes on to say that they do not necessarily have the same number of neutrons. And so the example it gives is neon. So neon has these 3 main isotopes. And so they all contain 10 protons, but then they have different neutrons. And that also means they have different masses. And so now we said, and this is for the mass of one atom, and we want to write this. So mass of our atom, and so that's going to be equal to the number of protons plus neutrons. And remember, that goes back to we said that each proton has a mass of 1 AMU, each neutron has mass of 1 AMU. And so that gives us a total mass of that one atom. And so for each of these, and again, notice how you report the different isotopes by then their mass numbers. So then we can say, right, this is neon 20 versus neon 21 versus neon 22. So that's saying the total mass. Then you could look up neon. Well, neon always has an atomic number of 10, always has 10 protons. Then we just have to determine the number of neutrons. And so now, based off of our formula, and then knowing that each one has 10 protons, so now we can say, well, neon 20 has 10 neutrons. Neon 21 has 11 neutrons. Neon 22 has 12 neutrons. Again, they all have 10 protons. Now, they all have different masses. And so we went over how to represent the isotopes. And so here is again our mass. So just mass is protons plus neutrons. And they use these symbol A for mass. Then again, there's our Z for our atomic number. So you have to subtract, get our number of neutrons. And so it can be written in different ways as well. So neon 20, you also might see 20 neon like that. So let's look at some other examples and a few other things. And so let's go over some other isotopes. So you have carbon. And so there are 3 main isotopes of carbon. So we have carbon 12. So this is the one we're most familiar with. And so let's do protons, neutrons, and electrons. So for carbon 12, we have 6 protons. That's our atomic number, right? We can go look. Now we have 6 neutrons. And then electrons, we haven't gone over explicitly, but we can write. So we've been looking at neutral compounds. So in a neutral compound, so without a charge, or in a neutral atom, we should say. So in a neutral atom, the number of electrons equals my number of protons. So we have 6 electrons. And so now if we look at carbon 13, so carbon 13, so now these are some fun facts. And so carbon 13 is also, so these are both stable isotopes. And so carbon 13 has 6 protons, 7 neutrons, 6 electrons still. And so carbon 13 is used for carbon NMR. So basically it allows you to see carbons. They use for C13 NMR. And so I don't want to go, like I said, I'll get too excited about everything. But just something to know about this. So carbon 13 is a 1% abundance. And so especially in the past, there used to be more difficulties in collecting these carbon 13 spectrums because, you know, let's say you had your sample, you put it in your little NMR tube, but you're really only looking at 1% of a sample in there because there's only a 1% abundance. So it's really, really small. Now, you know, modern technology, it's getting better where you can collect a carbon-13 NMR in under a minute, but it used to be, it could take 10 minutes to an hour, depending on an older instrument, for a good carbon-13 NMR. Anyways, probably half of what I said didn't make any sense to anybody, but I like to give a lot of fun facts in context. All right, so now our last isotope is carbon-14. Anybody know what that one is used for? I'll reveal it after we go through this. So protons, again, still 6. And then our neutrons, that's what's changing. So 8 plus 6 gives us 14. And then electrons, again, it's still neutral. So protons and electrons are the same. So 6 for that as well. And so you may have heard of carbon-14, since carbon-14 is actually radioactive. And so therefore it's used for carbon dating. So carbon dating can only go back a couple thousand or 100,000 years. So maybe like 500 to 50,000 for carbon-14 dating. So it has a half-life of about 5,730 years. But, usually it's used to date like human remains or other, organic specimens, trees, other life that you would find. So that's what carbon dating is used for. So it's used often. So you might, see it, or you hear it somewhere. They're talking about dating an old specimen. Right. So let's look at another isotope. And so let's look at bromine. And so bromine is interesting. And so I'm pulling up a chart while I also do this. So bromine is unusual in that it only has 2 isotopes. And so its 2 isotopes are bromine 79 and bromine 81. Let's see if we can do protons, neutrons, electrons for those. So take 30 seconds or so. Oh, what did I do? I was trying to post a link to something. I was trying to see if this chart is actually that useful. Well, I was trying to show this, but the website's a little bit misbehaving. I think it's more the engine. I was trying to find the bromine or something. There we go. I was having trouble navigating. All right, I'll have to find a better chart. Anyways, let's go back to this. So if we look at bromines, let's go look at our periodic table. And so bromine is 35. That means it has 35 protons. So we can put this down for both of them. And so now we have to pull out our calculator, or at least do some math. And so how many neutrons does bromine 79 have? We do 79 minus 35. And so we get 44 neutrons for bromine 79. And so then we should get 46 for bromine 81. So 81 minus 35. Just double check that. So 46. And then no charge on them. So electrons would be 35 as well for both. So that's interesting. And so now let's look at some other things. And so if we look at this mass on our periodic table, so what do you notice about the mass of bromine? And so it's kind of weird, right? So if you look at it, and what I'm getting at is, well, bromine's mass is neither one of the isotopes, right? So it matches with 80 roughly. So we could round this to 80, but that doesn't match with an isotope. So what's going on here? So there's a couple of different things to note. So the mass on the chart, on the periodic table, is an average of all the isotopes. So mass on periodic table, average. And so why I brought up this one is because it's really easy to see that, because you have, so for our example, right, the mass of bromine on the periodic table is, we'll just say 80 roughly. And that doesn't match with either one. But, and how we get the mass, it's, if we do this mathematically, so it would be the sum of every isotope. And so, right, the mass then of your isotope, 1, times the percent abundance of that isotope, right? And then et cetera. So going on and on. So if you had, you know, in the case, well, let's go back to carbon. So carbon is mainly carbon 12. So it's like 99% carbon 12, 1% carbon 13, and less than 1% of carbon 14. And so you just sum those up. So it's mainly, 0.99 times 12 plus 13 times, 0.01. Got to move the decimal place over twice. And so if we look at the average for carbon, it's just barely over 12. And so you see, right, that 1% of carbon 13 makes it 12.011 if we average, again, all our isotopes. So going back to our bromine, that means, and this is just kind of roughly then, so we have a mass of 79. And again, I mentioned bromine was unusual in that these isotopes are about a 1-to-1 ratio. So they're both about 50%. So it'd be 79 times 50%, so times 0.5, plus 81 times 0.5. And if we take those two numbers, and again, it's a little rough because I'm not using the exact AMU. And so that gives us roughly 80, which is again about what is on the periodic table. So that's where that comes from. And this will probably, I think it comes up in one of your labs where you have to add together the percent abundances of everything and calculate, different average masses. So this is the process you'll be going through. It's just when you get to that lab, and I'll go over it once that lab comes up, but you'll be keeping track of, sig figs and all that as you do the addition. All right, so see if you can take a look at this problem. So what's the atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons? And so again, post answers in the chat. And so let's try to figure this out. So we need to figure out our atomic number. And so that's 17 if I look at my periodic table. So 17, that means my mass is going to be protons plus neutrons. And so we said we had 18 neutrons. So now let's figure out our mass. So 18 plus 17. I think that's 35, but I just don't want to mess up my mental math this morning. So yep, 35. And so now it gives us our mass number. And so now we can write it out by 35, 17 chlorine there. So questions? And so now let's talk about, we talked about isotopes. Oh, before I forget, so I posted a link to Wikipedia, I think has a decent chart. So the other one I posted, the link is fine. It's just because it's fancy. I was having issues loading it and navigating it. But some things that I was trying to show, so you could drive yourself crazy or have way too much fun looking at this chart. So this chart shows every single possible isotope. And so of course, they've done a lot of research to try to make these happen. And so again, I was pointing out that bromine is interesting that it only has 2 stable isotopes. And so you can look at that here. And there it gives the percent abundances, so the exact percent. So not exactly 50-50, but really, really close. I mean, that was really close. So, and of course, you can look at all these other isotopes. We can scroll down to chlorine. I was having issues rolling with that other version. So here's chlorine. So we were just talking about 35 chlorine. And so chlorine has 2 stable isotopes, except that they are in about a 3-to-1 ratio. So 75% chlorine 35 and 25% chlorine 37. But again, if you want to look at all the isotopes, feel free. And then they try to give you, something like how long these species live. So some of them are extremely, short-lived. Sorry. Like some of these are just a couple of seconds. Anyways, that's for your entertainment. And so now let's talk about ions, which are just going to be charged atoms, or could be molecules. We'll later talk about charged molecules. And more specifically, so we could either have cations, and so cations are positive, and you can always rewrite that. So cat, and people like circle that plus sign. So our cation. And so if we have a cation, we have more protons than electrons. And so, how I like to think about it is I like to say that the charge or overall charge is equal to protons plus electrons, except, right, electrons are negative. So, even though you're adding them, right, it's almost like they should cancel out. Or you could think of like subtracting the electrons, however that works best in your brain. So, for me, I'm thinking of I'm adding negative electrons. And so, if we go back, to these scenarios, well, we said they were neutral. So my protons plus negative electrons, so 35 minus 35 is 0. So now for these, if they're positive, right, we can still think of it as protons plus electrons or plus negative electrons. And so let's do one. So let's look at magnesium 2 plus. So how many protons, neutrons, and electrons? Take 30 seconds or a minute or so. All right, what do we get? So protons, I'm going to pull up my periodic table. So magnesium here, 12. Let me write that down. So 12. And so this is another scenario I wanted to bring up just in case it happens. So for magnesium, right, we weren't given the mass. And so, and this might come up on your homework in a certain scenario. Well, let's say you're not given, the mass like we were in these cases. So if it doesn't say, then you usually just want to round your mass, right? Because we should get whole numbers for protons and neutrons when we're just talking about one atom. And so we weren't given an exact isotope. So we can just say, let's round it to 24. So 24 minus 12 gives us 12 then for our neutrons. And so sometimes you may find, a scenario, and this is where like there'll have to be a judgment call. It's like, where do I round? Or if for example, if you were given like the bromine problem, but you weren't given an isotope and you knew that there was, two isotopes, you can just say, hey, I'm assuming it's this isotope. And based off of this is what the neutron has to be. Otherwise, if you're given enough information, so if you're given, protons and neutrons, then of course you can figure out the mass. But sometimes, like in this case, I purposely did not give you the total mass. So we just did our best rounding guess. I would not penalize you for that. And so now let's look at electrons. And so again, a couple of different ways to look at it. We can set it up algebraically. So now my charge, so 2 plus is equal to protons minus electrons. And so now we can solve electrons equal 10. You can also, just think about it. Okay, well, neutral, there would be 12, 12 and 12. But if it's plus 2, I know I need more protons. So I'm going to have only 10 electrons. Let's try another one. Let's do, and so see if you can figure out protons, neutrons, and electrons for this one. All right, so let's look at this one. Again, post your answers in the chat. So protons. So we should be able to extract it from this. So remember, our atomic number should be at the bottom. If we're ever unsure, we can always double check. Okay, 16. 16 protons. So now my neutrons. Now they gave us a mass. So let me pull up my calculator. 34 minus 16. So 18 neutrons. And then electrons. Now we have a -2 charge on there. So 2 minus. And so again, we could do it algebraically. -2 is equal to, so protons plus negative electrons. So -2 equals 16 minus my electrons. And so now electrons equal 18 for my algebra. Or you can again start from the neutral. So neutral has 16. But now if we have -2, we have to be adding 2 more electrons. Now we should have 16 protons, 18 neutrons, and 18 electrons. Any questions about that? All right, so then we're going to take what I call our tour of the periodic table. So we'll take kind of a general tour, talk about some properties, but then we'll go back and kind of look at electronic structure and how to do electron configuration. Well, let's just start with our general tour. So we have all our columns here, or they're called families. And so these families, so hydrogen is kind of off by itself. So hydrogen is a little odd. And again, just kind of orient yourself with your periodic table. The periodic tables will also have different degrees of kind of, I guess, detail, we'll say, on this. So this one I like. It has a lot of categories. So notice, right, our hydrogen is different because it's off in this non-metal gas category. So it is a gas, it is a flammable gas. And so hydrogen, usually if we're in class, I like to blow up some hydrogen balloons. And so famously, there a bunch of hydrogen exploded in this Hindenburg disaster. So they filled it up with hydrogen. So obviously hydrogen is less dense, so it floats kind of like helium, except why helium is used now instead of hydrogen is helium is inert, so it's not going to explode, while hydrogen is very explosive. Just seeing if it talked more about that, just how isn't really. So it says might have just been some static electricity, so it's pretty flammable. Anyways, great pictures. Yeah, so it apparently was pretty fast, so 30 seconds. So if you ever look at a hydrogen balloon go up, it pops pretty quickly. And so, again, pretty flammable. And so let's think about that, or at least think about some other issues or what this means. So, hydrogen, some people have been trying to figure out how we can like run on hydrogen fuels or Toyota hydrogen cars. Have you guys heard of hydrogen cars? And so, of course, right, part of the problem is, well, how are you going to fill them up? And so, this is also why fossil fuels are so great. So, fossil fuels, they're a liquid. You can have a bunch of pipelines. I know pipelines get a bad reputation, but really, if you think about statistically what other methods there are, so of course, then you have to go by tanker or by ship. Those are more prone to disasters versus a pipeline. And so, but the problem is, so how would hydrogen travel? So, hydrogen, again, you have to condense it as a liquid. So, that's kind of difficult. And then to try to keep those pipelines chilled, that would not be reasonable. And then you would have a bunch of gas going through pipelines. So, it really has a lot of, tricky logistics still with hydrogen. Although, Toyota is still investing and banking on it. But again, we'll see what happens. So, hydrogen is by itself. And so now let's go to the rest of these before I rant too much about hydrogen and tell you all the fun facts. And so if we look at our key here, so all these pink elements here are called our alkali metals. And if you don't have that marked, I would write it down on your periodic table. So our alkali metals. And so why people know these or how they think of them is usually they're all water reactive. And so we'll revisit why. So right now we're just kind of learning our similarities. And this is also initially, before they knew about electrons and electronic structure and, any orbitals or anything we're going to talk about. That's all they had to go off of. Early chemists was how they react and what kind of compounds do they form. And so let's see, since I don't have you in person, let's see if we can watch at least a little bit of a video. So let's see.
Group 1 metals are very reactive because they have low ionization energies. One of the ways that indicates its high reactivity is the way that we store the metals. Group 1 metals are typically stored under kerosene or mineral oil to prevent or limit the reaction with the oxygen in the air.
Oops. Sorry, music playing. All right, so that was really important what he said, right? So that all these metals, this is also kind of a fun fact. So lithium and sodium you can work with in air. Potassium is right on the edge. So potassium, the problem is once you start slicing it, especially like a fresh slice of potassium, it has the risk of auto igniting in air. And then after potassium, you cannot work with it in air. So rubidium, cesium, well, francium is also radioactive, but these will react with the atmosphere. So they get really reactive really quickly. He mentioned a low ionization energy. So again, we don't know what that means, but we'll get back into the theory as we go through this. Right now, I just want you to appreciate the explosions.
Let's look at some of the physical properties for Group 1 metals. Lithium is an excellent conductor of electricity.
So they're going through a lot of experiments, but notice, right, it's shiny. And so as we do this, and you might want to pull this up. So I like this periodic table as well. So it's called ptable.com. And if it's what I like is that it kind of shows you the Wikipedia. It used to work a little better. Oh, here we go. And so you can click on it and see the pretty picture, right? So that's the thing that they all have in common. These alkali metals is they're all shiny. They're all pretty soft too. So that means like lithium. So there's lithium in oil. There's sodium. So all of these you can cut with like a razor blade. And so notice though, once we get down to rubidium, so in this Wikipedia picture, it's in a sealed ampule. So they seal it so it's sealed under an inert condition. And then you'd only want to open this in like a glove box or, unless you're looking to make an exploding YouTube video. So let's see, where do we get to the explosions here?
Metals are less dense than water. One of the things that we noticed is the fact that the lithium floats. Group 1 metals are less dense than water. We also see that the lithium reacts very rapidly with the water. This is a single displacement reaction producing hydrogen gas and lithium hydroxide. Lithium hydroxide is very water soluble and dissolves in the water. The hydrogen gas escapes.
And so that's just reacting. And let's write out the reaction of what happens. So we have lithium plus our water. And so then it makes hydrogen gas plus lithium hydroxide or any other hydroxide, right? So we can substitute this in for any other group 1. So now potassium plus water. And right now I'm not balancing the equation. I'm just kind of showing what they would make. And normally, so this is a base. So all these are bases, which we'll get into. So bases. So bases tend to have what's called this hydroxide group. But normally what I would have done if I were doing this experiment is I would have put an indicator called phenolphthalein in, and that turns pink once you start making a basic solution. So that would also help us see the reaction. It's just, oh, the water turns pink. So I know we're making hydroxide. Sorry, I lost my video. Let's look at sodium. Help if I hit play.
We'll go down the column on the periodic table in group 1 and look at sodium. Like the lithium, the sodium is stored in a mineral oil to minimize reaction with the oxygen in the air. If we remove a piece of sodium metal, we notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. Sodium is much easier to cut than the lithium.
You can notice how nice and shiny that is after you cut it. And so again, you can see the little gray oxide that he was talking about.
As we cut off the oxide layer, we can see the shiny metal underneath.
This guy's super thorough. Okay, let's skip down to the
We notice a much more rapid reaction with the water. Like lithium, the sodium is less dense than water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go down the column with group 1 metals, the melting point of the metal decreases. The reaction is very exothermic, which causes the sodium metal to melt. The metal contracts into a very compact spherical form. We can again test that hydrogen gas is being produced by this single displacement reaction by trapping the gas and testing its flammability.
That made a nice popping sound.
You know sodium hydroxide by adding phenolphthalein.
Now he adds phenolphthalein.
Phenolphthalein turns a purple-red color due to the presence of the hydroxide.
Let's watch him slice it.
Group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. Reacts much more rapidly with the water sodium. You go down the column, the ionization energy decreases and the metal reactivity increases. Reaction is.
And so notice with potassium, you should kind of see like a purple flame. And so sometimes with sodium, if you get sodium to flame, you should get like an orange flame, but doesn't always catch fire. It kind of depends on how big of a piece you use. So you saw with his piece, it didn't really catch. And so now we're looking at potassium. And so this one will spark more. And so you can kind of see those purple flames. So let's finish watching it.
Very exothermic. The hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding.
All right. And then he's just proving that it does the same thing. So making our base. So we could do the same thing for sodium and etc. All right. So if you want, you could probably search some more YouTube videos to watch people explode rubidium and cesium, but basically those just react pretty instantly. But let's keep moving on for the kind of interest of time. And so I might go a little long today because I'll probably have to end early tomorrow. And so now right next door is our alkaline earth metals. So notice there it's written, write it out again, alkaline earth. And so the key difference between our alkaline earth is now they tend to be much less water reactive. So some of them still react a little bit with water. So we could do, let's look at calcium in water. I don't know why this guy has a flame. I guess it's just for show.
Quickly using.
And so notice, right, when he added it in, it is reacting, right? It's fizzing. So we're still evolving some hydrogen gas, but it's not as explosive, right, as our alkaline metals. And even so, for example, like magnesium and water. So that doesn't do anything.
Metal still has are malleable. We also notice that there's no apparent reaction between the magnesium metal and the water. Magnesium metal has a much higher ionization energy than the sodium, and therefore.
And so notice reactivity, right? So this is a trend we're starting to notice. So reactivity increases as we go down. So remember the most reactive or cesium. So same thing as we go down, they get a little more water reactive. So magnesium does not react. Calcium, at least fizzes. And so that's something we notice. So sometimes with these group 2 metals, I like to say that they need a little acid. So magnesium does dissolve in acid. Now let me find that since now if we do magnesium ribbon and hydrochloric acid, and again, you may see these videos done by my wonderful coworker Dorothy later in the lab. And so you can see the metal up there, the magnesium strip. So pretty similar, at least reaction-wise, what was going on. And so we can write out our magnesium plus HCl. Now that would give us H2 gas plus magnesium chloride. And so we'll kind of see the salts and compounds they tend to make. So group 1, going back to this one, makes these kind of sodium chloride. And we'll get into the oxidation state and how those charges balance versus magnesium. It needs 2 chlorines since they're both -1. But again, we'll get into that. All right, so overall, again, we just said kind of less reactive. And so now in the middle, we have our fun transition metals. So personally, this is what I like. I like the transition metals. They all have fun colors because of their D block. But They're fun and complicated because of their D block, but we'll kind of, ignore them because they're D block. And so we'll just call them transition metals. We will go back and learn how to do at least some electron configuration with them. But overall, we won't talk about too much of their trends. They basically make pretty colors, is the quick summary of those, or, any impurities could be like colored gemstones come from impurities of these metals. And so now let's look at kind of either our group 3. And so now this starts to get a little interesting. So we have this stair step here. So this is our semi-metals here. And this separates our metals from our non-metals. And so as you go from left to right on the periodic table, they go from more metal character to less metal character. And this semi-metal staircase step kind of separates them. Now let's look at our P table here. And so these can be interesting. So boron could be used in like semiconductors. There's also a lot of research being done with boron. And of course, it's kind of this metally looking substance. And look at boron chunks, and it makes these compounds. So 3-coordinate, which is kind of interesting, which we'll talk about. So we go down. So aluminum, you've probably seen aluminum. So like aluminum sheets, that would be it. And then gallium. So gallium is a really low melting metal. For instance, there's this book, The Disappearing Spoon, where I guess you can play a joke on somebody. If you make a spoon of gallium, it looks like a regular metal spoon, but then if you put it into the tea, it will melt. And so here's elemental gallium is a liquid at temperatures greater than 29 degrees Fahrenheit, so it'll melt in your hand, which sounds cool until you have to work with it and actually try to melt it. So that's fun. Indium is below it, so it's also a pretty soft metal. So that's all these are metals. And so then we have thallium. So compounds of thallium are considered toxic. So you want to probably not work with thallium. So ideally, you don't want to work with thallium. I've worked with thallium myself. I didn't want to. I worked with a thallium compound, but in the end, it didn't work. So I didn't work with it very long. Didn't do what I wanted it to do. But here it mentions that they're highly toxic, and they can also lead to hair loss if you have thallium poisoning. And apparently, it's been used as a murder weapon, these thallium compounds. Right. That's thallium. So that's group 13. So if we move over to kind of group 4 here, so now that's carbon, silicon, germanium, and tin and lead. So of course, carbon, we mentioned we're carbon-based life forms. So carbon is generally black, like activated carbon. Like I was talking about those ice cream cones where people are eating like black ice cream cones. Y'all know what I'm talking about? Well, anyways, it's a kind of buyer beware. Although this one uses black food coloring. So I was going to say, there we go. here's a recipe. So this is what I'm talking about. So some places use activated charcoal to give it that black flavor. So you're not quite sure if, if you go to these boutique ice cream shops and you have black ice cream. So that it could be several things. So this mentions black food coloring, but I've heard some stories where if they use activated charcoal, yes, it is safe to eat, but it could make some people sick because activated charcoal, what it does, it's just able to absorb different compounds. So it kind of depends how you're using it. Some people use it and believe it helps with like detoxing or like symptoms of, let's just say, like lessening gluten allergies with activated charcoal. But by that same token, right, activated charcoal could absorb like nutrients in your body that are essential, or if you're taking some sort of medication, you might want to be careful because it could interfere with that activated charcoal. So that's kind of the thing to keep in mind. But some people get sick, even though, again, it's safe to eat, but they may feel ill if you eat activated charcoal since it is, interfering with your body chemistry. So everybody's different and everybody has different body chemistry. But that's my warning if you go eat black ice cream. So just be aware of what it might be or ask. And so then we have silicon. So, of course, silicon is used in chips and all sorts of manufacturing. Like I mentioned, there's a lot of chemistry research based on silicon to try to get it to be reactive, like carbines and carbon. And they're trying to do like silicon based life forms or like synthetic based, try to get it to do all the cool reactions that carbon can do. But again, not quite carbon. And so we go down silicons and then we have germanium. So again, is also a metalloid. And germanium is stable as a 2 coordinate compound. So that's kind of cool. And then tin. So tin is also toxic. So again, that would be compounds that contain tin are toxic. See, as long as it's so inorganic tin is fine, but then the organotin toxic compounds are toxic. So that's always a good distinction, and I always like to point that out. There is tin. And then lead. So lead is, of course, also toxic, and lead is considered a heavy metal. So there's no exact definition for a heavy metal, but it just tends to be things that bioaccumulate is kind of what it's thought of. Looking at our lead. So that's our group 4 over here. And then so group 5 is our nitrogen, phosphorus, arsenic, antimony, and bismuth. So let's look at those. Oops. And so nitrogen is a gas. So here it's condensed down in its liquid form. So again, you may have seen like big liquid nitrogen tanks. Sometimes they have them at like dealerships to fill up your cars now, your tires with N2. And if you come on Friday to our science expo, I will be making liquid nitrogen ice cream. So come. So nitrogen is, of course, super cold. And then if we go down, so phosphorus has different forms. So again, we went over, white phosphorus was unfortunately used in war. We have other forms of phosphorus. So arsenic is toxic, so it can metalloid. And so it's used in different compounds. Again, so it is toxic. So then used as herbicides and insecticides and a carcinogen. Again, metallic metal. And so then we have antimony. Again, also kind of this metalloid. Again, used in lots of alloys. And then bismuth. So now it's this brownish silver, radioactive. So just weakly. And so this is bismuth is used in Pepto-Bismol actually. So that is probably one of the most famous usages for it. And so now let's look at group 6. And so oxygen. So this is a great picture. So oxygen, of course, is a gas, but if you condense oxygen down, and so you can do this with some liquid nitrogen, and you can condense it in. So it's actually blue. So liquid oxygen is blue. Now, some safety facts. So liquid oxygen plus like an organic solvent, that's going to be a bomb. So this would be, a safety hazard. So of course, you want to be knowing when you're condensing liquid oxygen. And so why I bring that up is, this is kind of a nightmare for synthetic organometallic chemists or synthetic organic chemists who use, let's say, a Schlenk line. And let's say, you're using the Schlenk line. And what is a Schlenk line? I'm trying to get a picture that's not super crazy. So here's just kind of a general idea what a Schlenk line is. Probably a bad idea to click on it. Here's another picture. But basically it has, I can't tell quite from this picture which is which, but one of these gas manifolds, you put an inert gas through because this Schlenk line is for working with compounds that are air sensitive or water reactive. And so one of these Schlenk lines, one manifold is for like nitrogen. So usually you use nitrogen. If you're rich or have like a real need for it, sometimes you can use argon, but I think that's really just cost prohibitive unless you really need it. But it's very rare that you have a compound reacting with nitrogen. And then the other line is for vacuum. And so, generally in chemistry, you're dissolving things and pumping off solvents. But what can happen is if you accidentally have a leak open to the atmosphere and you're unaware of it, and then you're pulling vacuum. So then that means you're pulling vacuum on your atmosphere. So that's where you could come up with the danger of condensing liquid nitrogen. And so this is a trap. So this is a trap. This would be filled with liquid nitrogen. So you could pump off, your solvent and, pump it off. And of course, it would be condensed in this trap. But if you condense liquid oxygen, that would be scary because you don't want the organic solvent to melt and then react with your oxygen in there. So that'd be a bomb. And so that if you ever condense liquid oxygen in your trap like this, you just put your trap up and then need to evacuate the lab. So you'd have to let all your colleagues know, your PI know, hey, we got to go. Like we got to leave. So there's a bomb. And the vacuum pump will take care of the oxygen. So oxygen obviously has a pretty low boiling point. So ideally the oxygen will just be pumped off and then I'm sure your solvent will eventually go too because the nitrogen will only hold so long, but it's better to do that than the alternative. All right, so that's oxygen. And then I like to say, so, right, we have oxygen. So oxygen is not smelly, but the rest of these are smelly. So sulfur kind of starts off the smellies. And so sulfur, pure sulfur would not be smelly, but then like hydrogen sulfide can be smelly and other compounds like the mercaptan that they put in to natural gas to make it smell. So that's pretty distinct smell of rotten eggs. But it's all those compounds of sulfur that tend to smell. Of course, sulfur's yellowish, so pretty distinct. Then we have selenium. And so selenium compounds, again, start to smell. So they can also be toxic and give you weird taste if you were to ingest some. And so, and toxic. And then if we move down to tellurium, so now tellurium is even smellier. So if you get ingest some, which you would not want to do, so it's toxic, but it was metabolized and then gives you like this garlic breath, which is not good. But all the compounds, so these compounds are smelly. Let's see. Yeah, all those are fun. Let's see. There it is, tellurium breath. So yeah, you do not want to be exposed to that. Yeah. I think there was even a tellurium compound that led to an evacuation of a town. I was trying to find the story of the tellurium town evacuation, but it was some chemical that got released and then it was just super horrible. Yeah, they all smell bad. All right, so let's finish up. And so we mentioned the halogens are now over on the end. So halogens are fairly reactive and toxic. So this is liquid fluorine. So normally fluorine is a gas, and so fluorine is difficult to work with. So you would need like a fluorine regulator that is somewhat resistant to corrosion. And again, all these are toxic. So you want to be very careful when working with fluorine, and obviously making sure you don't have any leaks with your regulator. And fluorine can react with a lot of group 1 compounds. Here's some fluorite. That's cool. Oh, and look at this. People also died because of fluorine back in the early days, which is not surprising. So fluorine can form HF. So HF is a pretty nasty compound. So HF could dissolve the calcium in your bones. That's not good. Chlorine. So chlorine is also a gas. Again, difficult to work with. Sometimes you can generate chlorine gas and then use it. So that's kind of one of the more safer ways as opposed to like a tank of chlorine. And then bromine is actually a liquid. So bromine has a synthetic advantage. So organic chemists tend to like bromine. since again, it can be added as a liquid. It does start fuming and it can be an angry red fuming liquid, but it can still be handled. And it's also a great reagent, a good leaving group. And then iodine. I love iodine. So iodine is this really pretty violet, black, shiny metallic substance. And so what's really cool is it sublimes. So it goes from the solid to gas state to solid again. So that's pretty. Iodine, though, is a regulated substance now. So you can thank Breaking Bad for that. So iodine can be used to make meth, but kind of like bromine, it's got a lot of synthetic advantages. It's a good leaving group as well. And there's the iodine vapor. So iodine vapor can be toxic. So some of those clock reactions you have to be careful with because if you don't quench them properly, they do eventually release iodine gas, which is kind of scary. It's like this purple gas, but you know, the people you're demoing for may get excited. All right, let's wrap up today's lecture with the noble gases. So noble gases are inert. And so we start with helium. And of course, you can pass electricity through them. That excites their electrons and gives off pretty colors. So here's helium. We can go down. So neon lights. So that gives us that nice orange glow. Argon, krypton. And so now if you go down, so generally you don't find compounds of helium and neon. Argon, I think there are a few compounds. So it does form compounds under some conditions. I believe now they may have also made a few neon ones, again, under forcing conditions, but neon is pretty small, so it's hard to react with. Again, just physically, it's small, and we'll talk about that. But then once we get down, so krypton has some substances, so krypton difluoride. So even though, again, we said it's it's unreactive, it can still react. And then xenon makes some other compounds. So xenon difluoride and xenon tetrafluoride. So that's pretty cool. And again, just kind of looking ahead where we're going. So the noble gases, generally unreactive, but then these larger ones, they're just so big that essentially they're diffuse, and so they can make some compounds. All right, so so we said noble gases, again, unreactive generally. And you also have to remember, you know, why there's so many exceptions in chemistry is because we're always trying to push the boundaries and make new compounds and discover new things. They're always trying to break the rules and find exceptions. And so again, halogens. And so I usually just call these ones by their number. So I go by their other number here. So notice they have 13, 14, 15, 16. I usually call them group 3, 4, 5, and 6. All right, so tomorrow we'll continue on with then an electronic tour. So looking at our electronic structure and then going back and answering, you know, why are these so reactive? Yes, we saw that they react similarly, but why is that? And we'll keep kind of digging into that as we go throughout the course. All right, so again, ask questions. And I hope you enjoyed this video. And I look forward to seeing y'all on Wednesday to take a look at this electronic structure and start talking about electron configuration. All right, I'm going to end my lecture. I'll hang around on stream in case there are any other questions. Then I'll stop. Otherwise, I'll see y'all by email over the internet. Thanks again. Thanks again. Happy MLK Day.